Heat is energy. Temperature is an indicator of the amount of heat in a system. Heat can produce extreme temperatures and destruction when badly dissipated. The same heat, well dissipated by moisture and flow, remains cold and harmless. Phaco probes can produce heat by friction. The resulting temperature from this heat will depend on dissipation. It is temperature what produces tissue damage. Incisional thermal injuries are occasionally reported and are not related to any particular platform or technology. Corneal burns usually occur fast, degrading surgical outcomes. No clinical evidence has related torsional phaco with an increased risk of thermal injuries. However, some have suggested that warm zones seen with torsional at the back of the sleeve are produced by heating of the phaco probe by internal metal stress. Bare probes have very low infrared emissivity, making infrared imaging inaccurate to explore this theory. We designed a thermal transfer system to examine bare phaco probes in search of zones of self-heating by ultrasound. A thin film with emissivity near 100% and with low thermal capacity was incorporated as a thermal screen. An electromechanic system using computer control was built to put the thin film in contact with the probe shaft only between periods of oscillation to avoid friction. A syringe pump delivered exact flow through the handpiece aspiration port. An ice bath was used in some experiments to offset inflow temperature below ambient. Water spray from the vibrating tip had to be controlled using a collector system with a perforated membrane and strong aspiration. Ultrasonic activation of bare probes produced an evenly distributed temperature increase in axial and in torsional modes. We were surprised to find out that torsional activation did not heat up the shaft of the bare phaco probe more than axial. High US power and reduced flow produce more pronounced temperature elevations with axial. In all tests, the probe self-heating phenomenon described was more relevant with axial operation. No focal temperature increase was found in the shaft of the probes that could correlate with the warm zones observed at the back of the sleeve in torsional mode. These warm zones, with no reported clinical relevance, could be related to some polymer response to the acoustic field, but not to probe self-heating. Internal metal stress, if involved, would be more relevant in axial mode according to these tests. Surgeons manipulating a handpiece will apply force against the incision walls with the vibrating probe. The impact of sleeve compression at incision level was evaluated for torsional and axial modes. A different computer-controlled system was built to examine the thermal response of the probe sleeve complex under controlled load conditions and flow restriction. A special array was implemented to accommodate the sleeve distal end, allowing flow without constriction of the incisional zone. Force was transmitted to the surface of the sleeve using a 2.2 mm strip of thin film, emulating stress conditions occurring during real surgery. The system delivered pulses of compression and relief with precise force and timing. Flow was circulated by a dual syringe pump and was continuously monitored using a flow sensor. We found no references indicating the range of force a surgeon can apply to the walls of an incision during surgery. To find this out, we used the principle of operation of beam torque wrenches. An inactive probe with a reference mark was displaced laterally inside a micro-incision, and the resulting probe lateral deflection was recorded. The probe was then tested in the lab using the force control system. In this way, we obtained an estimation of real incision stress levels, useful for this and future tests. Experiments were performed in sequences of axial and torsional power using load pulses of fixed magnitude and duration. Ultrasound activation produced an elevation in baseline temperature. Adding load produced a further increment in temperature that was more relevant with axial than with torsional. Increasing power produced more temperature elevation at the simulated incision location with axial. Low flow was associated with higher temperatures, also with axial. In general, for equal settings, axial produced more heat than torsional in the incisional area. Axial power with a duty cycle ranging between 35 and 50% was found to produce temperatures comparable to those of continuous torsional. Beside the lower frequency, to explain these findings, we analyzed probe vibration in the zone of loading. Axial showed a simple back and forth displacement rubbing the sleeve. Torsional showed an undulating movement of the shaft with side-to-side displacements added to rotation. We speculate that the complex nature of the motion pattern with torsional could produce less friction and heat. These experiments were designed to sensibly detect differences in heat generation between torsional and axial Phaco terminals. In vivo, dissipation of heat by nerve tissues as well as fluid perfusion will effectively limit temperature to lower levels than those detected in these tests. A rigid wire bent repeatedly is subjected to plastic deformations heating up by internal metal stress. The theory of internal metal stress as a dominant source of heat only with torsional is challenged by these bare probe tests showing that self-heating is more relevant with axial. Differences in elastic deformation could explain greater self-heating with axial. Probes with a sleeve simulating incision conditions also demonstrated that axial produces more heat, especially under load. Heat produced by continuous torsional could be matched to a duty cycle between 30 and 50% using axial. Although we report that axial Phaco produces more heat than torsional, we believe that all modern Phaco platforms are safe, operated within recommended settings. Console sensors can detect situations that can lead to thermal injuries, such as low BSS or a dropped irrigation line. Flow-preserving features are available, such as the bypass port. Flow-restoring algorithms can detect and remove flow-limiting occlusions. Most thermal injuries seem to be related to an improper procedure. Things to avoid are mismatch of the incision size with the sleeve diameter and tip diameter, high US power and over-torquing of the incision, low irrigation and low vacuum, prolonged power during occlusion. The surgical team has to be familiar with the technology and alert to the environment. In the end, excellent tools can be operated in dangerous manners.